Gemini North just caught 3I/Atlas, the third known interstellar visitor with multiple companions, defying every expectation and confirming that it isn't traveling alone. For decades, experts believed these cosmic messengers arrive solo or scatter in chaotic fragments. But these new, independently validated points of light move together, organized and steady, a mystery that challenges our understanding of what truly enters from the stars. Could this be a fracturing comet or something engineered? The records and reputations of modern astronomy now hinge on what comes next. So how did 3I/Atlas shatter the script, and what does this cosmic caravan really mean? Throughout history, the most transformative moments in astronomy have started with a single, stubborn anomaly. In 1610, Galileo Galilei pointed his telescope at Jupiter and found 4 tiny points of light moving in lockstep around the planet. The world's best minds dismissed them as optical illusions or errors. Yet, as Galileo tracked their orbits night after night, the evidence became undeniable. Those moons shattered the old idea that everything in the universe revolved around Earth, forcing a new understanding of our place in the cosmos. Centuries later, the discovery of Oumuamua in 2017 and 2I Borisov in 2019 brought fresh surprises. Oumuamua, with its strange shape and unexplained acceleration, defied every prediction about what an interstellar object should be. Borisov, unlike any comet seen before, arrived loaded with cyanide and carbon monoxide, offering a chemical fingerprint from far beyond our solar system. Each time, a single observation was enough to unsettle the foundations of accepted science. These rare visitors aren't just curiosities, they are direct samples from other star systems, carrying clues about how planets and comets form across the galaxy. Every detail, every deviation from the norm, has the power to rewrite textbooks. When a new interstellar object enters the scene, astronomers know they are watching a test of their deepest assumptions. The lessons from Galileo's moons and the first 2 interstellar comets are clear. What starts as an outlier can become the new baseline. In this field, even one well-documented anomaly can force the scientific world to reconsider what is possible. As the story of 3I/Atlas unfolds, the stakes are nothing less than a redefinition of what it means to encounter something truly alien. Gemini North's first high-resolution frames of 3I/Atlas revealed a pattern that defied simple explanation. Alongside the main nucleus, several discrete points of light appeared, each maintaining a steady distance and orientation as the object moved across the sky. These weren't brief flashes or random specks. The spacing between each light stayed nearly constant over hours, then nights, and across different observing runs. The points did not scatter or blur with the usual chaos of debris. Instead, their arrangement suggested a kind of order, almost as if they were tracking together in a loose but stable group. Within days, a network of amateur astronomers joined the hunt. Using telescopes scattered from Hawaii to Europe, they captured independent time-lapse sequences of the same region. Their images, taken with different equipment and processed separately, showed the same constellation of lights pacing 3I/Atlas. These volunteers, driven by the rarity of an interstellar visitor, checked and rechecked their data for errors, scrutinizing everything from tracking logs to exposure timestamps. Each observer ruled out common pitfalls: no star trails, no pixel glitches, no cosmic ray hits masquerading as companions. The pattern persisted. The consistency between professional and amateur observations raised new questions. If this was an artifact, it was one that fooled multiple telescopes, detectors, and reduction pipelines. If it was real, then 3I/Atlas was not just a solitary wanderer, but part of a more complex ensemble. The anomaly was now on record. Multiple coherent points of light, confirmed across sites and nights, moving in step with an object from outside the solar system. The search for explanations would have to reckon with this stubborn, repeating pattern. Avi Loeb, recognized for his willingness to entertain unconventional hypotheses, called for rigorous, reproducible analysis, but cautioned against premature conclusions. Davide Farnocchia, a specialist in orbital modeling, contributed by examining whether the companion's apparent motion fit known cometary fragmentation patterns or hinted at something more organized. Natural fragmentation in comets follows a predictable script. When a nucleus breaks apart, fragments are ejected at speeds ranging from a tenth to tens of meters per second. The result is a scatter, bits of ice and dust tumbling away, spacing out unevenly, each piece tracing its own path. Over hours and days, this chaos becomes obvious. The fragments drift, some accelerate, and the cluster dissolves into a spray. Astronomers can track these movements, measuring divergence rates and mapping the growing distance between pieces. The pattern is familiar, irregular, dispersive, and quick to lose any sense of order. 3IATLAS refuses to play by those rules. The Gemini North data show companion points holding steady, locked in a geometry that barely changes from frame to frame. The separations between these lights remain consistent, even as the entire group crosses the sky at tens of kilometers per second. There's no evidence of the telltale spreading that marks a typical breakup. Instead, the arrangement persists, neither tumbling apart nor showing the kind of random drift that would be expected from debris blown off by outgassing jets or tidal stress. Measured against known fragmentation speeds, the companions are puzzlingly slow to diverge. If these were fragments, by now the spacing should have increased by hundreds or thousands of kilometers, especially given the object's high velocity and the time elapsed since first detection. But the points remain in formation, their movement suggesting a shared trajectory rather than independent escape. This coherence is at odds with the physics of natural comet breakups, where even the most cohesive clusters begin to unravel quickly. The geometry of 3IATLAS and its companions raises the first major challenge. If not a classic fragment train, what is keeping this ensemble together? The answer will depend on whether future measurements capture a sudden divergence or continued improbable order. Cometary green has long served as a kind of cosmic fingerprint. In most comets, the vivid emerald hue comes from dicarbon, C₂, molecules fluorescing when struck by sunlight. The signature swan bands near 516 nanometers light up the coma, making the green glow a reliable indicator of this chemistry. For 3I/Atlas, the story is less straightforward. Publicly released spectra from Gemini North and other major observatories show no clear evidence of a strong C₂ signal. Yet, some images, especially those taken through broad green filters, reveal a striking greenish tint around the nucleus. This tension, visual green without a matching C₂ line, has become a focal point for debate. Spectroscopists have combed through the data looking for alternative explanations. Cyanogen, Cn, can contribute faintly to the green, but its bands peak further toward blue. There is also the possibility of rare carbon chains or even unknown molecules fluorescing under solar radiation, but so far, no peer-reviewed spectrum has confirmed their presence in sufficient strength. The simplest explanation may be that the green color is an artifact of imaging filters or contrast enhancement, not a true chemical anomaly. Still, the mismatch persists in some processed images, fueling speculation about overlooked chemistry or the limits of current detection methods. Without a clear spectral line to anchor the green glow, the composition of 3I/Atlas remains ambiguous. If the coma's color is not from C₂, then astronomers are left searching for new candidates, molecules or dust grains that could fluoresce under the right conditions. Until high signal-to-noise spectra settle the question, the green anomaly remains an open puzzle, hinting at either an unknown pathway in comet chemistry or a subtle trick of light and instrumentation. For now, the color of 3I/Atlas is a question mark, inviting further scrutiny as the comet continues its journey through the inner solar system. At a distance where most comets remain frozen and still, 3I/Atlas began releasing water vapor into space. Measurements from the Swift satellite and ground-based observatories suggested activity at more than 3 astronomical units from the Sun, far beyond the usual threshold for water ice to sublimate. While some estimates place the outgassing rate in the range of 10 to 40 kilograms per second, the precise figure remains unconfirmed, pending direct detection of water or its dissociation products. What is clear, however, is that 3I/Atlas became active much earlier than typical solar system comets, which often wait until they are closer to the Sun before shedding their icy layers. This early and persistent activity points to an unusual internal structure. Standard comet models describe a loosely bound mix of ice and dust, riddled with pores and fractures. Such porosity acts as a network of thermal conduits, channeling heat from sunlight deep into the nucleus. Volatile ices, carbon monoxide, carbon dioxide, and perhaps water, can then escape through these pathways, driving jets and plumes long before the sun's rays are strong enough to melt water ice at the surface. A highly porous body can also withstand the stresses of rapid outgassing and sudden solar storms. Instead of cracking apart, the network of voids allows pressure to dissipate gradually, reducing the risk of catastrophic breakup. Some researchers have floated the idea that 3I/ATLAS could be even more extreme, a hollow or shell-like structure with most of its mass concentrated in a thin, rigid outer layer. In engineering, hollow shells are prized for their ability to absorb impacts and redistribute stress, protecting the core from sudden shocks. If 3I/ATLAS shares this architecture, it might explain its resilience through repeated outbursts and even coronal mass ejections observed earlier in its journey. The comet's ability to remain intact despite intense activity raises the question: are we seeing the upper limits of natural cometary design, or is there something fundamentally different about the way objects form in other star systems? For now, the evidence points to an object built to survive extremes, with its porous or possibly hollow nature acting as both shield and engine for its ongoing transformation. Every hypothesis about 3I/ATLAS and its companions must hold up to direct observation. The core question splits into two branches: natural processes or something engineered. If the companions are fragments, physics predicts a spray, pieces drifting apart, irregular spacing, and changing positions as outgassing and solar forces push them along. Over days or weeks, separation rates should climb into the range of meters per second, with each fragment tracing its own unpredictable path. On the other hand, an engineered formation would demand something entirely different: fixed geometry, nearly constant distances, and synchronized movement, with relative velocities much slower than typical cometary debris. This pattern would persist even as the group races through space at tens of kilometers per second. Observable differences come down to geometry and motion. Do the points diverge like debris, or do they hold formation as if bound by design? Each scenario leads to specific, testable predictions. Future measurements must track how these companions move, how their brightness evolves, and whether any show coordinated changes. Only by mapping these behaviors can astronomers sort natural from extraordinary, turning a mystery into a set of falsifiable claims. As 3I/ATLAS approached solar conjunction in late October, the object slipped behind the Sun from Earth's perspective, dropping to less than 30 degrees of solar elongation. For several weeks, ground-based telescopes lost their line of sight, creating a blackout window in the public data stream. This isn't just a gap in amateur skywatching, it's a multi-week period when only a handful of platforms, mainly those orbiting Mars, maintain any vantage at all. Mars-based assets from the European Space Agency, NASA, and China could, in theory, continue tracking the comet while Earth remains blinded by glare. Yet during this interval, official releases slow to a trickle. The pattern is familiar. After Oumuamua's conjunction, and again with Borisov, data held for calibration or review rarely reach the public in real time. Some researchers attribute the quiet to routine vetting, while others notice the same tightening of information flow that has followed every paradigm-bending discovery. As the blackout stretches on, anticipation builds for the moment when 3I/ATLAS reappears in December, and the question of its companions can be revisited with fresh eyes and new data. Confirmation or refutation of the 3I/ATLAS companion puzzle now rests on precise, testable observations. First, astrometric tracking must capture the positions of the nucleus and each companion over time, daily if possible, with sub-arc-second accuracy. If the companions are fragments, their separations should increase measurably week by week, with relative speeds in the range of tenths to tens of meters per second. If, instead, the geometry holds steady, distances locked, motion synchronized, then the formation scenario gains weight. Spectroscopic follow-up is essential. Repeated, high signal-to-noise spectra can confirm whether the elusive C2 bands, cyanide or other volatiles appear or fade as the comet rounds the Sun. Any shift in the chemical fingerprint, especially after conjunction, could reveal hidden processes or validate the green coma debate. Polarimetry and phase curve measurements will probe the surface and dust properties, searching for signatures unlike those of known solar system comets. Radar and infrared mapping, if achievable, could test for hollow or porous structure by measuring thermal inertia and mass distribution. Finally, after the blackout window, astronomers will compare the post-conjunction identity of 3I/ATLAS. Does the same pattern of companions return, or does the configuration dissolve? Each of these metrics provides a falsifiable test, clear, public criteria that will decide whether this interstellar visitor rewrites the rules or simply expands the boundaries of the familiar. Independent amateur observations and rigorous data reduction confirmed these companion points were not artifacts. Unlike typical comet fragmentation, this configuration remained coherent over several nights. Spectroscopic data revealed an unusual green emission, inconsistent with standard C2 fluorescence, and early water outgassing was measured at approximately 40 kilograms per second at a distance of 3 astronomical units, both rare for comets at this stage. Yet, the precise nature of the companions, whether debris, fragments, or something more organized, remains unresolved. Official data releases have slowed, echoing past delays with Oumuamua and 2I/Borisov. As 3I/ATLAS emerges from solar conjunction in December, new observations will test whether these companions persist or disperse. For now, the record shows a pattern that challenges current models. The evidence is clear. Interstellar visitors continue to confront us with phenomena that demand new questions, and only careful observation will provide answers.